Hey friends, let's start with objective 2. Let's see Verma, work power energy. So first question is, a heavy stone is thrown from a cliff of height h in a given direction. The speed with which it hits the ground must depends on the speed of projection. Yes. Must be larger than the speed of projection. Yes, as it is losing some potential energy. So it must gain some kinetic energy. Must be independent of the speed of projection. Yes, and oh sorry, must be independent of direction of projection, not speed of projection, so it is incorrect. Maybe smaller than the speed of projection. No, it is not correct. Option B is correct because whenever nothing is specified we should neglect air resistance. If air resistance is taken into account, D can also be correct, but usually we don't assume air resistance when it is not specified, so A and B are the most appropriate answers. Next is, total work done on a particle is equal to change in its kinetic energy always. Total work done by the part by all the forces is equal to change in its kinetic energy. It is always, because it's a theorem, so it is always valid. Option A is correct. So only A is the correct answer. B, C, D are wrong. Third is, a particle is acted upon by a force of constant magnitude which is always perpendicular to the velocity of the particle. The motion of particle takes place in a plane. Then follows that velocity is constant. No, velocity will change its direction. Acceleration is constant. Obviously no, acceleration will also change its direction. Its kinetic energy is constant. Yes, because speed is constant, because no work is being done by that force which is perpendicular to velocity throughout. It moves in a circular motion. Yes, as the motion is a planar motion, it will be circular. Otherwise it may be a spherical motion or a helical motion also. Okay, so in a plane the only motion possible with these conditions is circular. So D is correct and C is also correct. A and B are wrong answers. Consider two observers moving with respect to each other at a speed v along a straight line. They observe a block of mass m which actually moves a distance l on a rough surface. Which of the following will be same as observed by these two observers? Kinetic energy of the block at time t. No, kinetic energies uh, need not to be same because they are moving with respect to each other. So velocity of block with respect to both observers will be different. Work done by the friction. Work done by the friction will be different because for both the observers the displacement of the block will be different. You can have a look. Let this is observer 1 which is at rest. Observer 2 must move with the velocity v for time t, so it has displaced by vt, and the block has moved by distance l. For observer 2 the block has just moved l minus vt, so obviously work done by the friction will be different for both the observers. Okay, so we can say total work done on the block, it will also be different because total work done is nothing but kinetic energy. Acceleration of the block, yes, because both the frames are either there is no relative acceleration between both the frames because relative velocity between them is constant. So we can say the acceleration of the block with respect to both the frames will be same. Okay, so the only correct option is D. You lift a suitcase from the floor and kept it on the table. The work done by you on the suitcase does not depends on obviously the part taken. In this case, the total work done is zero because initial and final kinetic energy of the suitcase is zero. So the total work done is zero, and there are only two forces. One is the force applied by you, and another is gravity. So both must be doing equal work. Okay, kinetic energy final, initial are zero, so work done will be total work done will be zero. So work done by you is nothing but change in potential energy. So This is mgh no matter what path you take, so you will also be doing the same work, which is independent of part, time, weight of the observer, but obviously depends on the mass of the block. Okay, so a, b and d are the quantities on which it doesn't depend, so it will be the answer. The next is no work is done by a force on an object if force is always perpendicular to its velocity. Yes, it's correct. Force is always perpendicular to its acceleration. No, it can't be possible because force will provide you the acceleration. And C, the object is stationary, but the point of application of force moves on the object. Yes, because force on which point the point on which force is applied should move, not it should not change. The point should not change. Okay, so C is also correct. Force work done will be 0. The option D, the object moves in such a way that point of application of force remains fixed. Yes, this is also correct. In pure rolling, you will read it in further chapters. So in pure rolling, the work done by friction is 0 because it is acting at lowermost point, and that point is not moving instantly, or its instantaneous velocity is 0. So work done by friction while pure rolling is 0. You can also say uh, for justification of option C, put a finger against a wall, rub it. No work is done by your force on the wall because the point of application of force is changing. Actually, it is not moving. Okay, no work is done by your force. Obviously, there is work done by the friction from wall on your finger because your finger is moving. And in pure rolling, work done by friction is 0. Option, let's start with next question. A particle of mass m is attached to a light string of length L, and the other end of the which is fixed. Initially, the string is kept horizontal and the particle is given an upward velocity v. The particle is just able to complete a circle. The string becomes slack when particle reaches its highest point. Yes, it is correct. The velocity of the particle becomes 0 at the highest point. No, because if it becomes 0, it will fall down vertically. So option B is incorrect. The kinetic energy of ball in the initial position was half mv square equal to mgl. No, it is greater than mgl because there will be some final kinetic energy left. So the particle again passes through the initial position. Yes, this is also correct as it is moving complete circular motion, so it must move through its initial position. D is correct, A is correct. Let's move on to the next. The kinetic energy of a particle continuously increases with time. We can say the resultant force on the particle must be parallel to the velocity at all instant. No, it is not correct. It may be the case, but must is incorrect. The resultant force of the particle must be at an angle less than 90 all the time. No, it need not. Yes, as it is increasing continuously. So at all the time, work done should be positive. All DWs, small work done should be positive. So at every moment, force and displacement or velocity must be making an acute angle. Option B is correct. Its height above the ground level must continuously decrease. It's not necessary because it will take the case will happen only when kinetic energy is increasing at the expense of potential energy. Okay, so we can increase kinetic energy by some other mean also by doing some external work. So C is incorrect. Option D, the magnitude of its linear momentum is increasing continuously. Yes, as P is given by under root 2 mke and kinetic energy is increasing, and for a particle mass is constant, so we can say the linear momentum is increasing continuously. But this statement is not true for a system of particles, which will be which will be the next chapter. So for this chapter, this is correct. For a particle, this is correct. Okay, next. One end of a light string spring of spring constant K is fixed to a wall and other end is tied to a block placed on the smooth horizontal surface in a displacement, the work done by the spring is half kx square. The possible cases are, obviously the work done by the spring, if it is positive, then the potential energy of the spring must has decreased by this amount. So we can say the system has moved towards the natural position. Okay, the system must have moved to the natural position from compressed or elongated state. So the spring was initially compressed at by a distance x and finally it's in its natural length. Option A is correct. String is stretched by a distance x and finally was in its natural length. Option B is correct. It was initially in its natural length and finally in compressed position. No, it is incorrect. In option C, the work done would have been minus half kx square. And also in option D, the work statement is incorrect because the work done would have been minus half kx square. Okay, C and D are incorrect. A and B are the only correct options we have. Last one is a block of mass m is hanging over a smooth and light pulley through a light string. The other end of the string is pulled by constant force F. The kinetic energy of the block increases by 20 joule in 1 second. The tension in the string is mg. Yes, because as the force applied is F, so the tension will also be equal to F because the pulley is light, so tension is nothing but F. The next option is tension in the string is F. Yes, tension in the string is mg. No, it is incorrect because it will be slightly greater than mg because the block is moving upward. So B is correct, A is incorrect. Option C says the work done by the tension on the block is 20 joule in 1 second. Option C says that the work done by gravity is minus 20. No, both are incorrect because the total work done is delta Ke and that is 20. So both must be doing some work. Gravity must be doing some negative work and tension must be doing some positive work, which is greater than 20. So we can say both the statements are correct and we have only option B as correct one. Okay, enjoy.